right, how does a lumberjack sound?
Oh,
I'm a
I'm a
lumberjack and
lumberjack.
I don't care. I
Okay.
work all
Work
day
all
and I sleep all night. Are those the words?
sleep all night and I work all day.
That's right.
Cut
Sleep all
down
night and work all
trees
day.
and eat my lunch. Something, something, something.
Monty Python at its finest. Welcome everyone. Today's theme is lumberjacks. Why? Because we chopping logs. It is chopping logs time. You guys can't see that it's chopping logs time. Let me get this thing shared. Now you can see that it's chopping logs time. we got a tool over here, an axe.
Although splitting wood with an axe is actually like really difficult.
You need like, yeah, you're right. You don't use an axe. I guess you use an axe to chop down a tree, but to split wood, you put a wedge in it, right? And you take a I guess what's it called?
Sledgehammer.
A sledgehammer, yeah. And then that splits the wood. Yeah, that's the best way.
I tried to split a log once with an axe while we were camping, and it took like half an hour, and I still never did it. It was sad.
There are some axes that when you pierce the wood, like you have a log that you want to cut into firewood, I guess. You pierce it, then you can then take a sledgehammer and hit the top of the axe, causing it to split.
So you have like a wedge with a handle.
Exactly.
To get you started.
But that's not usually. Usually you get it started. You get a crack, and then you put the wedge in, and then you slam it with a sledgehammer. Logs. It's logs time. We're chopping logs. Actually, I think we're literally chopping logs. Look, we have log base A of U times V,
and then we're splitting it into
Oh my gosh, this is totally unintentional, everyone. We just wanted to do a lumberjack theme, but it is topical. All right, so we've been talking about logarithms. They are super related to exponentials. They are inverses of exponentials. We needed a function that was the inverse, so we called it logarithm. I think actually logarithm, logos. I think it's derived from logos, meaning like, I guess, logic. It's a thing in English class. It's a literary thing. And then arithmetic. I could be wrong though. Someone in their journal throw up, do some research and figure out why do we call it a logarithm? Because why do we call it an exponential? I wonder what the etymology of all of these things is. Etymology, the background of a word.
Actually, that was something that some of my students suggested, because we have a discussion board for suggestions of math journal inspo, and some people were suggesting the etymology of some math terms.
Ooh.
Yeah.
All right. And there's some really cool etymology with sine and cosine and tangent, which we'll get to later. Actually, we'll embed that discussion in one of our videos about why is it called sine, cosine, and tangent. All right. Before we get started, let me go ahead and add some syrup to my coffee, because I think that syrup is a thing that lumberjacks like. It's like lumberjack is a popular profession in Canada. I don't know.
It's all conjecture. We don't know any real lumberjacks.
It's like Buddy from what's that movie called?
Oh, Elf.
Elf, yeah. Add syrup to everything.
Buddy the Elf, what's your favorite color?
What is the answer? Syrup? I don't know. All right, let's chop some logs. All right, so we want to prove some log properties. Right? Apparently, it is the case, given here property 1, the product property, that you can take the product of two things. Example, you can take like log of 2 times 3, and that's equal to the log of 2 times, plus the log of 3. Like, is the log of 6 equal to log 2 plus log 3? Actually, let me do this real quick. I got some math going on here. Can you see this?
Whoa.
Log 2 plus log 3. Oop, not log. Log 3. That's 0.77. So like what number, 10 raised to what gives you 2 plus 10 raised to what gives you 3. So we're going to have fractions. Let's check out the log of 6. Same thing.
Whoa.
Right? So 10 to what gives you 6? So there's this idea of exponents. And I actually encourage everyone to pause real quick and try to figure out this on your own. But we are going to proceed in like 3 seconds, 2 seconds, and 1 second. Let's prove this fact.
All right. I think we should use the understanding that like a log and a exponential like undo each other. So maybe we can
Let me write that up
do
here.
something that leverages our understanding, our existing understanding of exponent rules, which we did. Oh wow, that was a long time ago. That was like maybe 2 months ago.
Mm-hmm.
And use some of those properties to help us with the log properties.
Because this looks like an exponential property. Product becomes addition.
Mm-hmm.
Like if I have a to the 2 times a to the 3, it becomes a to the 2 plus 3. These are rooted in the same like conceptuality. I don't know. All right, but I've written up here the undoing properties, the inverse properties that you mentioned. Log base b of b to the x is x, and log b to the log base b of x is x. When you compose two inverse functions, you get the identity function. Racer X. Do you know what I'm talking about? Racer X? Speed
No.
Racer? Okay, anyways, let's proceed. All right, so.
Very, very like Wakanda. I guess that's it here. Though.
That's this.
Yeah.
And I think you hold it to yourself. Log base A of u times v. We're trying to turn that into addition. How can we get these exponents that you want?
Well, we could either do log base b of b to the u, or we could do b to the log base b of u to rewrite u.
So log a of what'd you say? B
to the log base b of u. And that might help us more actually, because that uses the exponent properties that can use the exponent properties that we're familiar with. Or so we don't have log properties yet, so we can't use those.
So sorry about the dogs. I'm looking at this thing. And we have an a down here. Are you cool if I do a to the log base a of u?
Oh, sure. Yeah, that'll work, right? Because it doesn't matter what the base is. We can just make it the same as what we had already.
Are the dogs really loud?
Kind of loud, yeah.
Let me go ahead and pause for a second. All right, I think the dogs have stopped, so I've resumed. All right, let's proceed. So I want to make sure everyone understands that this is equal to u. We're cool there, right? Mm-hmm. A to the log base a of u is u. Because a to the log base a of anything is that thing. All right. Can we do the same thing with v?
I think so.
A to the log base a of v is v.
Mm-hmm.
Now we can utilize those exponent rules, right?
So we have a as our base. So then we can just add those two exponents together with the same base a.
Think about what we can do. So viewer, think for a second. How can you get what we wanted? Log base a of u plus log base a of v.
I think if you scroll up a little bit, that might also be clearer.
Zoom.
Oh.
Log base b of b to the x is x. Log base a of a to the thing is the thing. I think we're done, right?
I think so. I think that does the thing. For V's, Mr. Kirk, I see that you write it like a small check mark.
Uh-huh.
And I just want everyone to be aware that the way that I tend to write V's when I'm doing math is like that. I put the little tail on it. It's just so that I don't mistaken it for a check mark.
Mm-hmm.
But this is also partially just trying to make up for like kind of poor handwriting. So those are some things that I do to help out. I also, dash my sevens. So like I do like sevens like that. Bam.
Can you tell the difference between my U and my V?
I can. Yes.
What evil mathematician thought it would be good to use U's and V's together? Because I'm using U's and V's because it's been ingrained in like my brain and my soul. I've done so much math with U's and V's at the same time. We do it a lot in vector math as well. Why? But I've spent a lot of time trying to differentiate my U's and my V's. So hopefully, if at any point they're not distinguishable, scream at me. All right, so we
There's
got
also a lot of students like to do U's just like without the little tail. And so
Yeah,
I like to
like-
put tails on both so that it's clear to me which one is which.
Yeah, sometimes I do my V with like a curve to like make it look a lot different in terms of its curvature from the U. This is a big, long philosophical conversation about handwriting. Let's proceed. We got things to do. All right. The quotient property. Now that we've done the product property, I said this a second ago. I gave you guys 3 seconds to pause and try the problem. But now that we've done the product property, I really encourage every single person to pause and try to do this one because it's going to be very similar. Here's your chance to pause and try this proof yourself. All right, let's do it.
Cool. Well, I think we should use what we did before for our first step of our adjacent proof, where we have we change our U and our V into A to the log base A of U and log base A to the log base A of V.
Trying out your little whoop. Okay. And then I think we can use more exponent rules here, right? Same base, numerator, denominator. So we can do some subtraction. That is the skill here. We have A to log base A of U minus log base A of V. And then boom, I think we're done, right?
I think so, yeah.
These kind of cancel out in a way.
Pew pew.
Pew pew. Oh, it's been a minute since we did the pew pew. Sounds like a dance, the pew pew.
Or they get chopped.
Whoosh, whoosh. I'm not making the sound of an axe striking wood, but whoosh is the sound of the axe swinging through the air.
I see.
Boom, proof. All right, we have these properties, and these properties are going to be invaluable when trying to solve equations that involve logs. Let's proceed. The power property. This is almost like number one, but just a bunch of times. Like, I want to do a formal proof of this, but this is really just U times U times U times ... n U's, so like 1U, 2U, 3U, n U's. And then just using the product property n times. Combine them, you got the n. That's like a head start on this proof.
Yeah.
But I really like the use. Let me actually not erase that. I really like the use of this inverse property. Let's try to use that again to have a formal proof.
So can we try to write U again, the same old way that we've been doing that?
Yeah, so A, we're using the letter A, the number A, because it's our base, but this works for any base, as you said before. So A times log base A of U, that thing is being raised to the n, and this is all inside of that log that we've introduced. Oh no, this log was there the whole time. We've introduced the A log base A, because that's just U to the n, U to the n.
I'm gonna purple. So we do this part. What's inside the parentheses? Bam. Is U.
That is U, yeah. All right, so.
Oh, but this is a power to a power, huh?
That's exponent rules.
Yeah. So we just multiply.
A to the log A U times n. We just bring that n down, right? Just real quick, A to the 3 to the 2, that's just A to the 3 times 2. A to the 6, because you have A to the 3 twice. All right.
But we also have the commutative property of multiplication, right? Because log base A of U is being multiplied by n. So we can have n times log base A of U.
N times log base A of U. Why are you flipping the order?
Because it just looks nicer. Because I'm looking into the future, and I'm looking at the right side of what we're trying to show. We were trying to show n log and base a of u. And so how can we get that? We'll just switch the order around.
Yeah. It's really important to know where you're going. You don't get in the car and then just start driving. You know where you're going. And I think that's a good segue into the next one in a second, is knowing where we're trying to get to. So you switch that order because you know that you wanted this thing here. So let's put the n in front. This is the thing we want. How can we get rid of everything else?
Just chop it out.
Chop. Chop. Oh, and the log went away. So let me get rid of that.
Chop,
N
chop.
log a u. That's it. We're done.
Nice.
This is actually, I don't want to say it's the most important log rules. All the log rules are equally as amazing and important. But this one, I like this one.
It's pretty cool.
It says if you have an exponent inside of your log, you can bring it down to the front of your logarithm. Log base 6 of 7 to the 11 is just, I don't know why I chose those numbers. Bring that 11 down, log base 6 of 7. This also reinforces the idea that like log base 6 of 6 to the 11, let me just change that 7 to a 6.
Is 11.
And the 11 down,
times
log
1.
base times 1, log base 6 is 1. So it reinforces that chop, chop property that we already have.
Nice.
But that better be true because all of these are rooted in the fact that the inverses collapse on each other like a telescope. Sound effects make everything better. All right, we got one last property for you. We actually have 6 more properties after this one next time. But this is the last one that's going to take us through the beginning of our understanding of logs. Logs are exponents in reverse. And we got some properties we want to prove. Okay, so this is called the change of base property. It's called the change of base property because we're taking a log that has a base of b and we're getting rid of it. What is the base on the right-hand side here?
That base is 10 because we remember that from the other video. When we're lazy and we don't feel like writing something, then it becomes a base of 10. Actually, unless you're in MATLAB, I think empty log is natural log in MATLAB. But, you know.
Hey, everyone, it is. They're not. She's not wrong. I had this conversation with Mr. Shaver once because, of course, he's the physics guy. Yeah, whenever they write log, they mean base e because it ends up being a more useful log. But I was reading the textbook earlier about logs, and the Richter scale, the earthquake scale, is a log base 10 scale. It's a common log scale. So they do use the common log in application. But it turns out that in physics, e is just a way better number anyways. It has lots of cool properties that we haven't even scratched yet. So, but anyways,
it's also for decibels and stuff, right? It's a base 10 system.
Yeah.
For all you audiophiles out there.
And I think what's it called? Like frequency as well.
Oh, okay.
Like 440, the frequency 440 is the note A for musical kids. And that I believe that scale is logarithmic, but I could be wrong. I could be wrong. There's a journal idea. Learn. Be smarter than us. Anyways, how can we prove this?
I think there's when I don't know what to do in a proof, I try my identity properties. I try to either add 0 by putting something in and taking it away, or I try to multiply by 1 by multiplying by something over itself.
I like the second one better because we want a fraction. So we don't want to add anything. We're going to make things more complicated. Because when you add things, then you have to find a common denominator. Let's do that second one you said. Multiply by a fancy version of 1. What would be a logical thing to multiply by?
Well, log of b is a number, right? So if we just multiply by log of b over log of b, we should still be log base 10 of b. Yeah. Sorry, I mathed at you.
It's okay. Yeah, so we have the same expression. We've just multiplied by 1 over 1. Let's write this in a fraction form. I keep almost doing it. So we have like log b, well, let me actually write this. We have log base b of x times log base or log b. Okay. So we have the right denominator now. We need to turn this numerator into log x. We need to turn the numerator into log x. We have the right denominator. What rules do we have? We have the product rule. We can split it up. I don't see that being helpful here because all of our logs have a single term in them. Similarly, the quotient property requires 2 terms, and all of our logs have 2 terms in them. Can we use the power property somehow to simplify this numerator?
I think so, because we're multiplying. Right? We have log base 10 of b is a number. We can think of that kind of like our n.
Well, actually, wait. Can we think of the log base b of x as our n?
Oh.
And raise that. Wait, I see. We've raised it up. So log base 10 of b, and we're going to take this thing and take it to the exponent. Log b of x.
And that's lovely.
Chop, chop. Wait, yeah. These get chopped. Chop, chop. So wait, let me actually add my denominator real quick because I want to forget that. B to the log base b of x is just x. So log x over log b.
Hey.
Oh, nice.
Did we use, Mr. Kirk, did we use 10 at all in this proof?
I don't think we used 10 at all in this proof. Because we introduced the 10, but then the 10 just hung out on the bottom. And then up here, we brought the log base b of x to the exponent, not the log b, so the 10's not getting moved around at all. And then the b's cancel, but the 10's just still hanging out down here. The 10 is arbitrary.
So is this change of base, is this property generalizable to not just base 10?
I think so. Are you cool if I write this? Log base b of x is equal to log base 10 of x over log base 10 of b, but it's also equal to log base a of x over log base a of b.
Nice. So I'm just going to add in a's wherever I see logs.
Oh, yeah, down here. Let's look at this proof with the base a.
And
don't forget to bam, bam, chop, chop. Excellent.
The a's. I just wrote them down.
Yeah, they all just popped up.
Boom.
They're actually popping up as you wrote.
Oh,
Not
cool.
like not fluidly, but every now and then a few would pop up. So we have the change of base. So this is saying that like if I have log base 7 of 11, I don't know why I'm feeling 7-11 today. That's equal to log 11 over log 7. It's also
natural log 11 over natural log
base
7.
ln 11 over ln 7. Let's check it real quick. Let's see if I can get that calculator back up. Oh, did I close my calculator? Oh, no, you know what I did? It's right here. Boom. Log. Oh, this is actually, wait, how do I do a base 7 in the calculator?
It's probably in the math button.
Yeah, math.
I actually never tried because I just use change of base formula.
Yeah, I think that's a good point. The power of the change of base makes it really easy to
log base.
Log base. So not every calculator has this, but look, it just gave me that 7 of 11. I'm gonna get a number. Boom, 1.23. But if your calculator isn't as if you don't have a TI-84 plus CE like I do on my computer, you can just do log 11 divided by log 7. Enter. Same thing.
There it is. Boom.
Bada bing, bada boom.
Proof by example.
Proof by example. Oh, we did the legitimate proof.
That's true.
Right here. But we verified. We made more of an understanding of what we meant by this proof. The change of base. It allows you to, for some things, just utilize the calculator. Right. This will be a useful one when we do some more of our proof properties. Hint, hint. So when we have our next lesson, and you're thinking about how to prove a lot of these properties, we got 6 more coming at you next time. The change of base is going to be the power move.
The power move.
The charge attack. All right. Ah, you grabbed me. And you know what? Earlier, with a nice little tool. Earlier you like responded to me in a way that I was like, I wonder if she's crabbing me.
I'm crabbing you.
You have Crab Hammer. That's a Pokemon attack for my fans of Pokemon.
Oh, really?
Crab Hammer. It's an attack that Kingler knows. Anyways, and I think some other Pokemon as well, other crab Pokemon. So let's use these properties. Use the properties of logarithms to expand the expression below. I know as lumberjacks, this is what we want to do. We want to split things up. Here's my challenge to you, Mrs. Contreras. Can you split this up, but also make it so I'm log base 10?
I think so. I think we can do that.
All right.
Let's see. So that's equal to...
Are you going to write?
I can try.
Okay. We got an equal sign?
So now, because now you're going to crab me. I can feel it. So that equals what? With our log properties, well, if you want log base 10, I'll just try to get 10 first. So we got log of 6 times x to the 4th over 7y, log base 10 of that, over log base 10 of 5. Is that valid? Oh, the crab.
Oh,
I see it.
Dang it. I was trying to hide it. All right, so let me recap what you just did because everyone else's video was watching me crap you. All right, so you changed the base right away. Nice. So you got log of the argument over log of the base. Cool. I'm cool with that.
In the numerator, I'm gonna have log of 6x to the 4th minus log of 7y because of the subtraction, or because of the division that gets a subtraction, which is property, 2?
Yep.
And then all of this is over log base 10 of 5, and that's really bad log, but that's okay. Let's see, what else do we have? Well, we have multiplication, so maybe we can take care of the multiplication. So we get what? Equals log of 6 plus log of x to the 4th minus parentheses log of 7 plus log of y.
Let it drop so we can see it. Boom. Awesome.
Oh, and then I forgot my denominator. So
never drop the, it's like dropping in like a baby, you know, you don't want to drop the baby, you don't want to drop the denominator.
I think dropping a baby is definitely worse than dropping a denominator.
I don't know about that. I think that's an opinion. I really appreciate.
You can undo dropping a denominator, just writing it in. You cannot undo dropping a baby. Mr. Kirk.
I very much appreciate that you threw those parentheses in there because I know that it's a common mistake to split up that log 7y into a minus log plus log y. Only the first thing.
But we need to remember the distributive property, right?
That minus is hitting both. I think there's one last thing we can do though.
Yeah, because we have log of x to the 4th. So we can take this, we can just pull it in the front, which I guess I will rewrite because that's the responsible thing to do. I'm going to do 1 over log of 5 times all of this because I don't want to get burned for dropping the denominator. And we have log of 6 plus 4 log of x minus log of 7 and minus it's very squished now, minus log of y.
That happens.
Okay.
And there's just enough room to not do the change of base, but you did the change of base like a pro, so.
Just did it up top.
Can one be a pro?
I knew what the
math?
goal was.
Yeah. Yeah, you did know what the goal was. So.
What are some limitations on what our values can be?
Well, let's see. We can't have negative things in any of our logs, right? Because if I imagine the log graph, it never goes to the left of the y-axis. So x can't be negative.
Well, can x be negative? Because if you look in the original expression, if you plug in
So
a
if
negative,
you plug in x, yeah. So I'm looking at the end,
to
but
the
what I
fourth.
really need to be doing is looking at the beginning, right?
Mhm.
X is totally allowed to be. So this is a really good point to make. Like if you think, everyone think back to like 5 months ago. Not true. 2 months ago when we were doing rational expressions, the thing that matters is the thing that I give you, which is log base 5 of 6x to the 4th over 7y. So x can be negative because it'll just get raised to the 4th and we're cool.
But x can't be 0, right?
X cannot be 0 because log of 0 does not exist.
Because we get an asymptote there.
Okay. However, but in addition, y cannot be negative, right? Because there's no exponent there.
Exactly. Yeah, I think so.
So y must be strictly greater than 0.
Strictly greater than 0, which takes care of not having a 0 in our denominator in our original expression as well.
Yeah.
But
there we go.
I don't know. I'm trying to bring that back. It's okay.
So this final expression is a little misleading because x is allowed to be positive. I think we should throw an absolute value on that x.
Boom. Oh wait.
Yeah.
Boom.
Sounds good. All right.
Cool.
Let's go ahead and do. Oh, look what I did to you!
Oh,
I
more
crabbed
crabs.
twice because the first crab didn't get it.
Crab.
Crab. All right, so I'm gonna go ahead and erase my crabs, because I want
So
that
we're
space.
trying to condense. So that means that we are unlumberjacking these.
You're
We're unchopping them.
Well, so when you cut down a tree, what should you always do?
I don't know.
Plant another tree.
Oh, okay.
So we're creating a tree here.
I see.
All right, so let's see. Can I do this one?
Sure.
I don't want to be left out of the fun. Okay, so we have 2 log 6. So that's just like log 6 plus log 6, and then I can use the exponent rule in reverse, right?
Mm-hmm.
Or log 6 times log 6, log 6, 36. And then I have a minus log x here. Let me just deal with these. Let me just rewrite them. You know, I'm actually going to, instead of being obnoxious and splitting the log 6 into 2 log 6s, for the log 3 log y, I'm just going to use the exponent rule.
Nice.
Okay, because there's different ways you can think about this. Is the point I'm making.
Feel obnoxious.
All right, so I need to be careful of these negatives because of PEMDAS, rule of operations, all that jazz. So I'm going to go ahead and factor out that negative just to stay safe. But if I was doing this, if I didn't do this factoring thing that I'm doing, I would need to combine these 2 things before these 2 things. Just because you move from left to right in math. All right.
Yes.
So I'm going to go ahead and go up here. Let me combine these 2 things. So I got my log 36. And then I'm going to combine. So the sum of logs becomes the product inside the argument. So I have log x y cubed. Then I'm going to do some subtraction. So it's going to be 36 over xy cubed.
Sounds good.
Boom. Do you see any mistakes in my work? I don't think so.
Well, what are the limitations that we have?
Let's see. We have So this is actually an interesting thing to think about, because if x and y are both negative. Oh wait, but I got to go back to my original claim. Is the beginning thing is what matters. Because in my final expression, if x is negative and y is negative, and they're both negative, and we're cool. But that contradicts my original expression. So x can't be negative. X must be strictly bigger than 0, and y must be strictly bigger than 0. And I believe that's our only 2 restrictions.
Yeah, looks good to me.
All right, let's solve some logarithmic equations. That's what the rest of this video is all about.
Let's go.
I don't think there's any reciprocating going to happen. Inside jokes.
But what if we try? We could try to reciprocate. What's a way that we can reciprocate? We just put a do we put a negative in front of the log? Would that reciprocate it?
Yeah, well, it would reciprocate the thing inside the log. Here's a rule that we're going to do next time. Log A of B is equal to 1 over log B of A. If anyone wants to try to prove that, like we did earlier, there's a rule that we can. There's some
reciprocator. We need to make like a little icon for the reciprocator.
We need like maybe that's the name of the crab. Reciprocator the crab. All right, let's keep going. All right, so we're solving logarithmic equations. And can you read for us this property of logarithms?
We have if log base A of m equals log base A of n, that implies m equals n.
Awesome. I think a good analogy for this property is if a squared equals b squared, does that imply that a equals b?
Well, -1 squared and +1 squared are both positive ones, so I don't know about that.
It doesn't, right? And this goes back to what we talked about a long time ago with functions. Logarithms are a one-to-one function. So if the outputs are the same, the inputs must also be the same. So we're cool when we're solving logarithmic equations to set the arguments equal if the bases are equal. And in this problem that we've been given here.
So if we have the bases are equal, like if we have 2 to the A equals 2 to the B, because like we're talking about logarithms are one-to-one, so that means that their inverse is also one-to-one. So then if we have like a base 2 to the A power equals a base 2 to the B power, does that mean that our A and B are equal? Does imply. Is that what it does imply?
It does imply. I was trying my handwriting, and I'll write does not up here. Does not imply. All right, so we're taking advantage of that one-to-one-ness of functions. All right, so these have the same base, so their arguments are equal.
So we can just like break them out of logarithm jail.
I think another way to do this, and we're going to talk about this in a second, is you could also like raise both sides to the 7.
Brilliant.
7
to the log base 7. Chop, chop.
Chop, chop. Chop, chop. And we just get x squared plus 4x minus 15 is equal to x plus 3. And we know how to solve this.
We do.
Let's just do it.
Draw a graph. No, just
kidding. Draw a graph. Yeah, I mean, graphically solving is a thing. I use it all the time. Desmos is the best. Free, beautiful math. But let's go ahead and solve this the factoring way. Subtract some x's.
Combine like terms.
Minus 18 is equal to 0. And then I believe this is going to be got 1 and 1. 18, 2 and 9, 3 and 6. It's going to be one of these.
I think 3 and 6. And which one needs to be negative?
We need it to be more positive than negative because of this positive sign here.
So the smaller one needs the negative.
Yeah, boom.
You know, we talked about that in maths today.
Awesome.
Yeah.
Factoring is just...
Well, we talked about at positives, like when we're doing a negative plus a positive, then the bigger like magnitude number gets the sign.
Zero product property, zero product. Zap. Oh, I'm going to use that for the rest of my life. Zap.
But there's no A, so it's
-6. We are such fools. We got -6. So we got 2 answers here. Legit. Awesome.
Not legit, Mr. Kirk. We need to make sure those answers work with the thing that we're doing. Does it work in what our original thing is?
So I think what we've done is we figured out 2 values that make the arguments equal. So if I plug 3 in, I'm going to get 9 plus 12 minus 15, which is 21.
So it's okay.
But it's going to be 6, and then 3 plus 3 is 6.
Okay.
So the log base 7 of 6 is equal to log base 7 of 6.
That sounds good to me.
And we plug in the -6, we're going to get -36 positive 36 minus 24 minus 15. That's going to be -3. We plug in -6 in the other side, we get -3. So the arguments are equal. But what are you saying?
We broke the logarithm. Yeah, the domain of our logarithm function is positive numbers.
Positive real numbers, yeah. I wonder if you could put complex numbers into a logarithm. I wonder what that would look like.
Whoa.
I don't know. This lesson is riddled with journal ideas. That's all I'm saying. All right, so what did we learn here?
We learned that if our bases of our logs are the same, then they can just go away, because when we raise like that base, if we use that as the base for our exponential thingy, then chop chop, they go away. So our arguments that are inside our logarithms are equal. But we need to be very careful, because our domain for our logarithm function is not all real numbers. So even though what might be inside our functions, we might have like multiple solutions, they might not all work. So we need to check. Plug it in.
Let's keep it in the back pocket. Plug it in, plug it in. All right.
Do kids still know about that?
I don't think so. The clapper. Wait, no, that's not the clapper. Plug it in. Plug
No,
it in.
that's the this is the air freshener.
All right, so here we are. We got some more equations for you, and hopefully logarithms will help us solve situations like this. All right, so I don't know. I'm feeling like we should just kind of get that exponent on its own. What do you think?
Yeah, that sounds good. So
-8.
-8 divided by
4
4
times. Recognize that that 4
2 squared
is not part of the exponent.
It's good old parentheses,
Okay.
helping you out.
The parentheses won't always be there. Divide by 4. How do I deal with this?
Well, 4 is 2 squared, so you're okay. So it's like 1 over 2 squared.
Oh, I see you solving some equations over there.
I'm just like low-key doing stuff on the side.
all right, all right. How about you finish up your problem? I'll finish up my problem, and we'll look at each other's answers, like we did previous class. I like that a lot.
Sounds good.
2 to the x. 2 to the. Or this is 1/2 squared. 2 to the -2. Oh, x -2. What rolls down hills alone or in pairs and over your neighbor's dog? What fits on your back? It's great for a snack. It's log. Okay, so you're done. Cool. I'm gonna check out your answer.
Cool.
I ended up getting x equals -2.
-2. Let me see. I'm just gonna plug that into your equation. Make sure that makes sense to me. We got 4 times 2 to the -2. That's 4 times 1 over 4. So that's 1 plus 8 is 9, and that equals 9. So I'm happy.
Excellent. Right, over here, you subtracted 6. You isolated that exponent. But you wanted to get rid of you wanted to bring down that x in the exponent. So you took the log of both sides.
Log base 3.
Log base 3 is, yeah.
Base 3.
And so that's just chop chop. Log base 3 of 3 of x to the x is just x. You've brought down, there's the right word. You've brought down the x. And then the other side is just log base 3 of 34, which is 3 to the what gives you 34. That's going to be some number between 3 and 4. 3 cubed is 27. 3 to the 4th is 81. So it's going to probably be closer to the 3 than the 4. I'm going to go ahead and like just add this option as well. Keep us thinking about it. Let's keep going.
Oh, change your base.
Yeah, change your base. Let's keep going. All right, how about you do which one do you want to do, 6 or 7?
I'll do 6.
Okay, I'll do 7.
All right. I'm going to go back to Kermit the Frog.
Oh, snap. What have you done to me here? I'm going to take the log base 5 of both sides.
That's why I gave you that one.
Because I'm just going to talk out loud. Because taking log base 5 of both sides is going to get rid of the 5. It won't get rid of the 2, but it'll at least get rid of the 5. Then log base 5 of 2 to the x, I'm going to use my exponent rule, bring that x down. I'm over here, x minus 1 is equal to x log. Oh, log base 5 of 2, that's just the number. That's 5 to the something gives me 2. 5 to the, probably like 1/2-ish. Because 4 to the 1/2 gives me 2. So 5 to the 1/2. So I'm actually going to write that as a number in front of my x. Subtract to the other side. This is getting a little bit crazy.
That sounds like it's getting crazy.
I don't like that you gave me this one.
I like that I gave you that one a lot.
2 different bases. All right, I'm going to factor my GCF out. X, and I'm going to, x times what gives me x1? X times what gives me log base 5 of 2x, log base 5 of 2. And then I think I'm done. X is equal to, I'm going to divide both sides by 1 minus log base 5 of 2. 1 minus. And I'm going to get, my final answer is, I'm going right to the bottom of the page. This one's a doozy.
A doozy.
Doozy. So 1 over 1 minus log base 5 of 2. So it's 1 divided by 1 minus 1/2-ish. So it's going to be like 2-ish. 1 divided by 1/2. So it's going to be roughly 2, something around there. And then if I go up here and I plug in something 2-ish, I'm going to get 5 to like the 1-ish is equal to 2 to the 2-ish. That's kind of like, that sounds about right. 2 to the 2 is 4. 5 to the 1 is 5, so they're close. And if I just move those numbers a little bit, I'm going to get something that's equal. I think I'm good with my answer. All right, can we talk about yours and you can take a look at mine?
Cool. I'm not quite finished. I just got my last thing because I was partially listening to you, and
Yeah.
that was
I'm sorry.
really throwing me off. Well, it was fun because it was like it's like multitasking with my brain, but it's also challenging.
Yeah.
Bam. So what I did was well, I looked at 4 and 8, and I thought to myself, hey, those are both powers of 2, so I can save myself from all the headache that Mr. Kirk has to deal with, and I can rewrite those as 2 to some power, and then use some exponent properties. So
Boom, boom.
4 is 2 squared, and then 8 is 2 cubed, and then I just multiply my exponents, have the same base, so I use that property that we just learned about, but I wrote it out with log base 2 because I really liked that, what you said about that, Mr. Kirk, where it's just very clear once you do that you get your exponents are the same. And then when we have 2 lines, then we just solve. And I didn't really feel like multiplying 3 times 18 because just kind of felt really lazy. So it's okay. You just break 18 up into 10 and 8 and then multiply a little bit easier. So that's where that 30 and the 24 come from. And you might have done that in your head, but I wrote it out because it's late and I'm tired. So then we got 54 that we moved over to the left side. We got 2x that we got to take away on the right. And then just divide and you get 64 over 7. And that's like something that seems like a reasonable input. I didn't check it, but.
Can I check real quick?
Sure.
I know that number's a little bit bigger than 9, right? 9 times 7 is 63. So if I'm over here, 4 to the 13, oh, that's big. And 8 times, it's 9. So 9 times 3 is 27 minus 18 is like, this is where I'm messing up. 27 minus 18, it's like 9-ish, right?
27 minus 18 is 9, yeah.
Yeah, so like if my number is roughly 9, I believe that 4 to the 13 is equal to 8 to the 9. There's extra things going on there. That feels right. That feels totally right. It's a reasonable answer.
It vibes.
Yeah. If you got something negative, I might be like, but that number that feels legit. Take a look at mine.
Wow. So you have different bases, and it looks like you tried to just get one of them away. So you took log base 5, and that's nice.
I wouldn't have been able. The reason why I had to do that, I think, is because 5 and 2, there's no real way to write them in terms of the same base, like you did. So you had that nice 4 and 8. They are powers of the same number. 5 and 2, they're both prime.
They're just doing their own thing. So yeah. You used some login on the left, log base 5, which is nice, and then you brought down the x, which is in the exponent for the 2. That seems legit. Now you have x minus 1 equals x times log base 5 of 2. And log base 5 of 2 is just some number. 5 raised to whatever power that equals 2, something small. And so that's fine. You just threw parentheses around it so that you make sure that you remember that that's just a coefficient. It's not like a beautiful coefficient in terms of like ease of use, but it's a number. And then combined like terms, got a division happening because you factored. Love it. Looks good.
Good stuff.
Yeah.
Let's go ahead and proceed. Let's knock this one out of the park. We're just solving logarithmic equations. You know, swing, swing.
Swing, swing.
Swoosh, swoosh. I don't know, like an axe.
Oh, chop, chop.
Chop, chop. That's what it was. All right. So, what about equations? So, we used logarithms to solve exponential equations. How can we solve logarithm equations? Maybe we can use exponentials.
Oh, I was going to say factor, but
well, factor is usually always the answer. Now let's factor out a 3 of both sides.
Mm-hmm.
I'm going to be obnoxious and actually do that.
I mean, that works, right?
Yeah.
You just divide by 3 on both sides.
Yeah. Get rid of the common factors on both sides.
Mm-hmm.
Got a 2. How can we resolve the log by using exponentials?
Well, can we do the snail?
We could do the snail.
5 to the 2.
5 to the 2, but
which is effectively 5 as the base for both sides. We have
snail it.
5. Yeah.
5 to the. Did I do it wrong? I think I'm supposed to do this, right? It doesn't matter.
Yeah, 5 to the
5 to the 2. The whole point of the snail is to tell you which way to go. 5 to the 2 is the argument. Mm-hmm. I like what you did there also. If you 5'd it up.
5 it up.
You raised both sides to the 5, and that's essentially what we did up here. I guess we logged it down, which is what a lumberjack does. This theme has been so topical. It was totally unintentional, but we logged both sides to bring down the exponent. Here we're exponenting both sides to get rid of the log. We're 5ing it up. And then I think the final answer here is going to be 25 is equal to x plus 2. X is equal to 23.
Seems legit. Does that work?
I think so. 23 plus 2 is 25. Log base 5 of 25 is 2. 2 times 3 is 6.
Oh, easy.
Now we got 3 problems here. We're actually, this one down here, we're going to make a whole separate video about that one because if you look at it real quick, Alex deposited $2,000 into an account that pays 4%. This is a compound interest problem that will then be solved using the things that we talked about in this lesson. That's a lot. We're gonna give that its own pedestal. We're gonna solve that one later in its own video. But we think it's important that we talk that one out and not just leave it to you guys. So we're not gonna get to it in this video, but we will get to it. Let's look at 9 and 10. You want to do one? I'll do the other.
Sure.
And we challenge everyone here to try to solve one of these. Normally in class, we would pause and give you guys time to try to solve these. So this is where you try to solve them while we do the same. Which one do you want?
Well, I got to choose the other one, so I feel bad. I should let you choose.
I want 10, I think.
Okay.
Because that has a lot going on in number 9. I want number 10. Maybe I'm gonna regret this.
Okay. Sure. Just to clarify, like it was totally intentional to be lumberjacks with the log one, right? Like when I remember that we were doing logarithms, that's why we were talking about doing a lumberjack theme.
That is not why I thought we were doing.
Oh, really? You just like really like lumberjacks?
Let's go for it. Let's do lumberjacks. So everyone, Mrs. Contreras chose the theme. I did not realize why we were choosing this theme. I'm just like lumberjacks. I am game. I got the beard. I got the flannel.
All right.
All right. So now I know that was intentional. Apparently,
it was super intentional because you were like, we're doing logarithm properties. Like, oh, okay, we should do logs. Oh, lumberjacks. We should do lumberjacks.
No, it's fine. Now I know. At the end of the video, 50 minutes later. All right. I'm gonna solve number 10.
That's fair.
I'm Xing it up.
I'm gonna pull the 2 up, and I'm gonna divide. Oh wait, I totally did that wrong. I divided wrong. I'm supposed to divide inside the log. Hang on.
Let's relish in this. Let's relish in this real quick. Go back. I want to see the mistake. I didn't get to see the mistake.
Can I undo it? I can't undo it. No.
I love mistakes. I
had,
think they're worthwhile. What went wrong?
I had log base 6 divided by log base 6. Bam. So that's what I had, and it's wrong because when we're using our log properties, we don't keep the log, like we don't like trail the, drag the log along, but we do the operation inside the log. So that was my mistake. That I kept the log for the second part where I should have divided inside the.
Yes, it should be log of 6 of those things divided.
Yeah.
That's the beauty of the log rules, is it takes multiple logs and turns them into singular logs.
It unlogs it. But now I'm going to erase it and fix it. Then I'm going to 6 it up.
All right, I got my answer. Let's see what you got.
Nice.
6 it up, and then you're done, right?
Yeah, I mean, that's a satisfactory answer, right? I don't have to simplify it anymore.
I think you should, but I mean, like, at the end of the day, simplifying is like preferential. I actually had a 16 to the 1/4 as well in my problem.
Whoa. 16 to the 1/4, that's 2, right? Okay.
2, 4, 8, 16, right? For some reason, I don't have memorized that 16 to the 1/4 is 2, but I do have 16 to the 32 to the 1/5 is 2. If that makes any sense. That doesn't make any sense. I know 2 to the 5th like very well for some reason. 2 to the 4th, I got to think about it a little bit more. Wait, did you just get 8?
I think so.
Guess what I got?
Did you get 8?
Hey,
Whoa!
we're so easily impressed. All right, so let me look at what you did. You brought that 2 up into the 4. You brought that 1/4 up into the 16. Then you used our subtraction property of logarithms, the quotient property, but in reverse. So the subtraction property turned into quotient. You have 4 squared over 16 to the 1/4, but you also have that both sides are the same base log. So we can set the arguments equal. And then you simplified your numbers. 4 squared is 16. 16 to the 1/4 is 2. 16 divided by 2 is 8. There you go.
Oh.
I don't feel like plugging it in. It's probably right. I don't see any mistakes.
It seems right.
Check out mine.
Okay. So you got a base of x. And so did you say ahead of time that x cannot be equal to 1?
Well, I didn't say that. I thought about that. That's why I wrote it there in the right.
Okay, cool. So you have x, you're xing it up, and then you got a chop going on because you have x raised to the log base x, so that just breaks that 16 free. So you have 16 equals x to the 4/3, and that makes sense. And then you're trying to get rid of the 4/3 as your exponent by raising to the 3/4, because power to a power, that's going to, as long as you're raising to the reciprocal of your rational exponent, is going to cancel out, and that's really nice. So then you get 16 raised to the 3/4 power, and then you think to yourself, which one do you want to deal with first? 16 cubed? Heck no. 1/4? Yes. 16 to the 1/4, which you said was 2. Cube that, and you get 8, so x equals 8, and you didn't forget your x, which is very responsible. Nicely done.
Thank you. Thank you very much. As well with you.
Thank you.
All right. We did logs. We chopped. This was an intense video.
I also like how many colors we used.
I know. Yeah, this is a very colorful day, a very very fun day. I like this lesson a lot. I hope that everyone else did. Let's go ahead and stop my share.
And then they can like and subscribe. And
don't forget to like and subscribe. Give those pennies. Any words of wisdom or last word before we vanish into oblivion?
Oblivion? We'll just stop recording. We're still going to be here.
You mean we don't just exist in a box? In a digital box? No one's seen me. None of my students have seen me physically yet. So
it's true.
It could just be a very smart AI.
I'm not sure if AI is quite at the point of hilarity that we are at. So,
It's true, yeah. AI
we're like too funny to be AI.
We are too funny.
Yeah, genuine intelligence, not artificial.
Yeah.
I think just going back to what you were saying earlier about how we really like mistakes and we like thinking about them. And I was very quick to erase mine, but just really like looking at the things that we do wrong, thinking through them about what went wrong here, and then not like being sad about making a mistake in front of people on video for everyone to see for the whole internet. Now there's documentation of Ms. Contreras making a mistake. Not a terrible thing. Mm-hmm. It's totally okay. And it's something that we learn from. I think that that's something that I would like us to acknowledge.
Yeah, because I think the mistake that you made there at the end is a common mistake. To take the subtraction of 2 logs and make it the division of 2 logs. What we really want, the subtraction of 2 logs becomes the quotient within 1 log. Common mistake. So I think it's good to see that. I think I was saying this to one of my classes the other day too. So all the classes listen to this. But one of the best things about having in-person school, and I know we don't have in-person school right now, but one of the best things is being able to get up in front of people and make mistakes and then learn from each other's mistakes. So that's one of the things that, we're trying to emulate here, right? You're going to make mistakes. We're going to make mistakes. And it's important to see each other's mistakes and to be comfortable in that, with that. So thank you for those wise words, Mrs. Contreras.
You too, Mr. Kirk.
I think that's a good journal topic. Write about maybe a mistake you made in math that made you learn.
What a prompt.
Yeah, cool. All right, ready?
Cool. Yeah.